All right, so as I was saying, today we'll be looking at what we call thermal expansion. And from the definition or from the statement itself, we can see to say this is expansion that is dealing with thermal properties. So we'll look at four different sub topics that I may call objectives, because at the end of today's class, I want us to be able to define what linear expansion is all about, and the equations related to linear expansion, and the same about area expansion, volume expansion, but also volume of spill. So this will be today's topic under topic one, which we called thermal physics. Okay, so to begin with, I would love to discuss with you what thermal expansion is. So from the statement itself, we can see we have thermal here, then we have expansion there. And I'm sure we see these things every day, but we just don't pay much attention to them because we don't know the phenomena behind them. So you notice some days, even in power lines, you're going to notice that it's a very hot day, they are going to be sagging down a bit more than it will be on a very cold day. Those differences are actually seen due to thermal expansion. The same is also going to be noticed when you put, let's say, water in a glass bottle. You're going to find that after some time, if it is supplied with heat, the bottle will start overflowing. What has happened there? It's the phenomena of thermal expansion. So we see these things in every day, and they are also used in different parts of engineering, whether it's designing of a bridge, the railway lines. You're going to find that there are some spaces left in the middle. Why? It's because they are leaving some room for thermal expansion, because as materials, let it be solids, liquids, and gases, are exposed to heat, they are going to start expanding. There will be expansion taking place when all kinds of matter are exposed to thermal energy, or are exposed to an increasing amount of thermal energy. That is that on thermal expansion, ladies and gentlemen. So in words, I can just define thermal expansion as the increase in dimensions. The increase in dimensions of a substance when its temperature increases. Of a substance when its temperature increases. That is how we can define thermal expansion. And this kind of expansion exists or takes place in different dimensions. We've just generalized it to say it's the increase in dimensions of a substance, but this increase in dimensions can take place in different kinds or in different ways. You're going to find that sometimes the thermal expansion takes place in only one dimension. Sometimes it is going to take place in two dimensions, whilst sometimes it is going to take place in what? In three dimensions. Sometimes it is going to take place in three dimensions. And when it takes place in one dimension, we call it linear expansion, which means it is only, or the expansion that is taking place, it's only taking place in one direction. And you're going to notice this mostly in things like roads, a metal rod. You're also going to notice it in rails, but also in wires. So when the expansion is in one dimension, we call it linear expansion, which means the or the substance that is in question is only expanding in one direction only, and we call that linear expansion. You can experience that in roads, rails, but also wires. Then when it comes to two-dimensional expansion, we call it area expansion, this one here. When a substance is expanding its two dimensions, for example, or the example that I can give here is a metal plate. You're going to find that I have a metal plate here. It has its length there, but it also has its width there. So if it is expanding in its length at the same time expanding in its width, that means there is two-dimensional expansion that is taking place there. And when there is such nature of expansion that is taking place, we call that area expansion. Then when it's three-dimensional expansion, as usual, I'm sure you can guess about this one. We're going to call that expansion in volume, because the size of a substance is expanding in all the three dimension, which will be the length, the breadth, but also the height of that particular substance. Hence, expanding in volume. So we call that volume expansion, depending on the number of dimensions that the expansion that is taking place is in. So that is that, ladies and gentlemen. We can now look at area expansion or linear expansion in detail. We can now look at linear expansion in detail. Okay, so I've already talked about this to say when we're talking about linear expansion in definition, we're just basically talking about the expansion that is taking place in only one dimensions or one dimension. And the good example that we can talk about here is the length of a particular substance. That's why it is seen in things that we only concentrate on their length, such as roads, a rail, but also a wire. We focus on the length of these particular materials that I've mentioned here. So when there is linear expansion, that means expansion is only increasing the length of that particular material, or mainly it is focusing on the increase in length of that particular material. And why is that coming about? It's because we know that as temperatures are increasing, the atoms that make up a particular element usually vibrate with larger amplitudes. So that takes, or that helps in the increase in length of materials. The average atomic spacing also increases, and also that eventually leads to the increase in dimension of a particular material. So when it's this kind of expansion that we're talking about here, that means we are describing linear expansion. And we can actually explain this type of expansion using an equation. So how do we find, or how can we find how much has a particular substance has increased, or how much range, or how much length a particular substance has gained after being supplied with thermal energy, or after its temperature being increased? We use this particular formula, which is change in length will be equal to alpha multiplied by initial length of that particular material multiplied by the change in temperature, like this. So we have this change in length, and we know to say when we have delta or change in something, that means there are two things involved. There is the initial of that particular substance, but also the final, where is this? There's the initial magnitude, but also the final magnitude. So we know to say when there's change in something, that means there are two things involved. There's, I'm trying to write L. I don't know why I have T in my mind. That means they have final length, but also there is initial length involved. So in other words, we can express this formula also as final length minus initial length being equal to alpha multiplied by initial length multiplied by the change in temperature, of which the change in temperature will also just be final temperature minus initial temperature. That is the equation that we can use to find how much length a particular substance is going to gain after being subjected to a change in temperature, which we've indicated here as T final minus T initial. So what is this alpha that we have here? Because I can see this is the only strange thing that we have in this particular equation. We have change, or we have delta L to represent change in length. We have L0 there to represent initial length. First, we have delta T to represent change in temperature, where we've said the change in temperature is just T final minus T initial, but also delta L is equal to L final minus L initial. Then we have L initial there for initial length. Then we have alpha. Now, what is this alpha actually talking about? Okay, so alpha is what we call the coefficient of linear expansion. Let me just write it down here. Coefficient, there's double F, coefficient of linear expansion. So what does it mean when we say the coefficient of linear expansion? Anyone who has an idea? This is a coefficient of linear expansion. What does it mean when we say that? Okay, so basically we can just describe it or define it as a coefficient that will give us the measure of how much a material has expanded per unit length per degree temperature rise. Hence, even its unit of measurement is just per Kelvin. You can say per Kelvin, which is K to the power 1, to the power minus 1 rather. We looked at units of measurements. So if I write K to the power minus 1, I expect everyone to know what that means. Or C to the power minus 1 like that, which means, which is basically just over K or over degree Celsius. So the coefficient of linear expansion just gives us how much a particular material, because it's different in each and every material, but it is going to give us how much that particular material is going to increase per unit length each temperature rise. That's why we're giving it its unit of measurement as per Kelvin or per degree Celsius. That's the coefficient of linear expansion. So we're going to notice that the larger the coefficient of linear expansion, the larger a material, or the more a material is going to expand. The larger the coefficient of linear expansion, the more the material is going to expand, and the 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 lower the coefficient of linear expansion, also the lower the expansion is going to take place. So this just gives us that particular coefficient, and it gives us the expansion characteristics of each particular material. That's why I've explained to say it's different in each and every material that you're going to look at, because each and every material is going to expand at a different rate, or is going to expand to a different size when subjected to a temperature change. So that is about the coefficient of linear expansion. We can talk about area expansion also, which is just two-dimensional expansion. Okay, so we can look at area expansion. And area expansion, the theory or the main idea is also the same. We've already explained how area expansion is taking place. It's just the two-dimensional expansion of a material. For the example that we have given is a metal plate, where you have your length, but also the width of that particular material. So you're going to notice that the width will be expanding, whilst at the same time, the length will be expanding when this particular material is subjected to a change in temperature, or a temperature rise to be specific. So how do we calculate the change in area, or the increase in area, when the temperature of that, or are surrounding that particular material has been raised? We say change in area, delta A, change in area is equal to gamma multiplied by initial area multiplied by change in temperature. So you can notice to say everything has remained the same. Here, the delta A is just giving us the change in area, final area minus the initial area. Then we have the initial area also here. Then we have the change in temperature, which is basically T final minus T initial. Then we have gamma. So gamma is also a coefficient of expansion. But since we are dealing with area expansion here, this is also specifically talking about the area expansion. So it's just giving us how much the area of a particular material is going to increase per unit area per change in temperature. So this gamma is also related to the alpha that we described in the concept for linear expansion, such that gamma, which is the coefficient for area expansion, is equal to 2 multiplied by alpha. So 2 times alpha just gives us the coefficient of area expansion of that particular material. So this is all about area expansion. Or if you want, you can also write this equation as the final area minus initial area being equal to gamma multiplied by initial area multiplied by change in temperature, which will be T final minus T initial. So you can use this equation in case they've told you to find the final area, or they've told you to find the initial area. That means you basically have to replace your delta L with these guys that we've indicated here. Then you can proceed with your calculation. So this is about area expansion. We know to say the unit, or the SI unit for area, is the meter squared. So even if you've been given different units of measurement, you're supposed to remember that if you're discussing about area expansion, that means you're dealing with the units of measurement for area, which is the meter squared, as the SI unit for area. So that is all about area expansion. We can also talk about the expansion of volume. Volume expansion. Okay, so when there's volume expansion, it's also the same theory, or the same concept, where there's three-dimensional change in the size of that particular material after it has been subjected to a raise in temperature, or to an increase in temperature. So this is going to take place in to gases, solids, or liquids. So long as that particular material has a three-dimensional shape, that means it can be subjected to three-dimensional expansion, which we term area, or I mean volume expansion. So uh, the formula for calculating volume expansion is also the same. Delta V, which is the change in volume, will be equal to the coefficient of volume expansion, which is beta, multiplied by the initial volume, V0, multiplied by the change in temperature, T. So we have change in V, or delta V, as V final minus V initial, as usual. Then we have the coefficient of volume expansion, beta. Then we have the initial volume there, whilst we also have T final minus T initial there. That is to explain all that is contained in this particular formula. So as usual, again, This coefficient of volume expansion is also related to the coefficient of area expansion, but also the coefficient of linear expansion, such that beta is equal to 3 times alpha, of which we know to say alpha here is just the coefficient of what? Of linear expansion. So beta is equal to 3 times alpha. That's the relationship between the coefficient of linear expansion. Also, when it comes to the coefficient of area expansion, we say d gamma is equal to 2 times alpha. And we've also said beta is equal to 3 times alpha, like this. So how or what will be the relationship between the coefficient of area expansion and the coefficient of volume expansion? So we can just say the coefficient of volume expansion will be equal to 3 over 2 will be equal to 3 over 2 gamma, like this. So that is the relationship between the coefficient of volume expansion and the coefficient of area expansion. And this is the formula that you're supposed to know. You're supposed to understand this formula and not just memorize uh, the values that you're seeing there, because sometimes they might change. So make sure you understand the concept before memorizing anything. So that is about volume expansion. We'll look at some examples later, but we can also look at what we call volume of spill. So the phenomena of spilling, I'm sure we know what spilling is. You're going to notice that if I have, let's say, water in a tank, I can give an example of a tank here, or even a gas. One thing you're going to notice is that gases and liquids expand more than solids. Gases and liquids expand more than solids. So the thing that causes gases and liquids to expand more than solids is that these guys usually have a bigger coefficient of expansion. Bigger coefficient of expansion. Like that. So you're going to notice that if I have a tank here, let's say the tank has a volume capacity of 20 liters. The tank has a volume capacity of 20 liters, but also you've added a liquid in here in the tank of capacity 20 liters, which means you have filled this tank to its full capacity. Then if you apply heat to this tank, you apply or you apply a change in temperature, a positive change in temperature, which means you are increasing the temperature surrounding this tank, which is containing a liquid. You're going to notice that the liquid that is inside the tank will start spilling outside the tank. It is going to spill like that as you are raising the temperature. Why is that? It's because the volume of the liquid that is inside the tank has expanded at a higher rate, or has expanded more than the expansion of the tank. We know to say even the tank that will be made up of a metal, or in short a solid, is also going to be expanding, but it is not going to expand in the same way as the liquid which is there, because naturally liquids and the gases have higher coefficients of expansion as opposed to metals. So this is what we call the phenomena of spilling, like that. So How can we calculate the volume of spill now that we've understood what we are discussing here? How do you think we can calculate the volume of spill? The volume of spill will be equal to what? We had the same initial volume of the tank and the initial volume of the liquid which is inside the tank. These guys are the same, which means the initial volume that we are going to include in this formula should be the same because everything here is similar. So the V initial of both the water or the liquid that is inside the tank and the tank itself is the same. The only difference between these two is the coefficient of volume expansion. So if we want to find the volume of spill or the volume of the liquid that has spilled out of the the solid tank, we're going to say volume of spill will be equal to the difference in the coefficients of expansion between the liquid and the solid. So we're going to say this will be equal to what? This will be equal to the coefficient of volume expansion of the liquid, which is the bigger one, minus the coefficient of volume expansion of the solid, which will be the smaller one in this case, multiplied by what? Multiplied by initial volume, which was the same in this case, multiplied by V0 multiplied by change in temperature. So that is how we calculate the volume that is going to spill out, or the amount of liquid that is going to spill out of that particular solid tank due to the differences in their coefficients of volume expansion, hence calculating the volume of spill. Is there anyone with a question up to this particular point? Anyone with a specific question up to this point? Okay, so if there's no question, that means we can proceed to look at some examples quickly. And we have question 1, which is saying a thin spherical shell of silver has an inner radius of 1.6 times 10 to the power minus 2 meters when the temperature is 25 degrees Celsius. The shell is heated to 155 degrees Celsius. The coefficient of volume expansion of a spherical shell of silver is 57 times 10 to the power minus 6 per degree Celsius. What is the change in the interior volume of the shell? What is the change in the interior volume of the shell? So they've given us the initial radius here of this spherical shell. Then they've given us the initial temperature as 25 degrees Celsius. They've given us the final temperature as 155 degrees Celsius, but they've also given us the coefficient of volume expansion, which means this is beta. They've given us the coefficient of volume expansion and they want us to calculate the change in interior volume, which means we're supposed to calculate delta V. So how do we calculate delta V? We say delta V is equal to beta multiplied by initial volume multiplied by the change in temperature, like that. So what is the change in temperature here? We know to say change in temperature is equal to 155 minus 25 there, which will be equal to what? Which will be equal to 130 degrees Celsius. 130 degrees Celsius. But if you notice, in this question, they've only given us the radius here, the initial radius, whilst they want us to calculate the change in interior volume. So if this is the initial radius, what are we supposed to do? We are first supposed to calculate the initial volume, V0, using this information that we have. And since this is a spherical interior, this is a spherical substance, what are we going to do? We can calculate the volume. We know to say volume of a spherical substance is equal to 4 over 3 pi r to the power 3. So this we are going to use this information to calculate our V0, which will be equal to 4 over 3 multiplied by pi multiplied by the radius, which is 1.6 times 10 to the power minus 2. Then I'll put power 3 outside there. That means my initial volume will be equal to what? Let me just plug this into my calculator. My initial volume is 1.72 times 10 to the power minus 5 cubic meters. That is my initial volume. So if that is the initial volume, then I can just get this initial volume and plug it into this equation that I've written here in order for us to calculate the final volume of this interior. So I'm going to say my delta V will be equal to the coefficient of linear expansion, which they've given us here to say it's 57 times 10 to the power minus 6 per degree Celsius multiplied by the initial volume, which is 1.72 times 10 to the power minus 5 multiplied by the change in temperature, which we've calculated to be 130 degrees Celsius. So that means our change in volume, when I plug this into my calculator, is going to be equal to 1.27 times 10 to the power minus 7 cubic meters. That is going to be our change in the interior volume of this spherical shell. Is there anyone with a question? Anyone with a question? Okay, so if there's no question, let's proceed to the next example, this one. And question 1 says define the term volume expansion. So anyone who can define for us what volume expansion is? What does the term volume expansion mean? Anyone who can define for us volume expansion? What is volume expansion? We are from talking about this just a few moments ago. Okay, so it's the increase in volume. The increase in volume of a substance when subjected to temperature change. When subjected to temperature change. That is what we call volume temperature. And specifically, this temperature change that we're talking about is the raise. So when it has been subjected to a rise in temperature, the expansion that is going to take place in the three-dimensional area of this particular object is what we call volume expansion. And question 2 is saying by how much will a steel rod Question 2 is saying by how much will a steel rod By how much will a steel rod 2.5 meters long expand when heated from 28 degrees Celsius to 60 degrees Celsius? The coefficient of volume expansion of steel is 3 times 10 to the power minus 5. So what have they given us? They've given us a steel rod. And if I mentioned to say when you are talking about a rod can only expand in one dimension, so which means we're talking about linear expansion here. So they want us find the expansion of this steel rod, which has an initial area of, or an initial length of 2.5 meters. There is a change in temperature, which will be 60 minus 28. Then there is a coefficient of volume expansion, beta, which is equal to 3 times 10 to the power minus 5 per degree Celsius, like this. But if you notice, the coefficient of volume expansion cannot be used to calculate linear expansion of this particular rod. That means from this coefficient of volume expansion that they've given us here. We are supposed to deduce the coefficient of area expansion. And remember, we said the coefficient of volume expansion is equal to 3 times the coefficient of area expansion. So if we've been given this guy and we're supposed to calculate area, that means our alpha, or I mean, we were supposed to calculate the coefficient of linear expansion. We're going to say alpha is equal to the coefficient of volume expansion, which in this case is 3 times 10 to the power minus 5 per degree Celsius over 3, like this. This is how we're going to calculate the coefficient of linear expansion. They've provided us with the coefficient of volume expansion, but we have to deduce the coefficient of linear expansion such that we can calculate the change in length, the one-dimensional change that this steel rod is going to experience. So from here, we can now bring our formula for linear expansion. We'll say change in length will be equal to alpha, of which the alpha that we have here is 3 times 10 to the power minus 5 divided by 3 multiplied by the initial length, which is 2.5 meters, multiplied by the change in temperature. So change in temperature is T final minus T initial, and this is going to be 60 minus 28, like that, which is 32. So I'll plug in my 32 there. Then we can plug this into our calculator to find the change in length, which is the linear expansion of this rod. So if I plug it in, I'm getting 8.0 times 10 to the power minus 4. 8.0 times 10 to the power minus 4 meters. That is all, ladies and gentlemen. Or if you want, you can say this is 0.8 millimeters. It's one and the same thing. So that is all, ladies and gentlemen, on what I had prepared for us today. We've discussed linear expansion, area expansion, volume expansion, but also volume of spill. And we've looked at different examples to make sure we solidify on the conceptual knowledge that we've just gained. So at this particular point, is there anyone with a question? Okay, if there's no question, that marks the end of today's class. You can stay blessed. Until next time, thank you for coming.